Hello, everyone. I'm a machine learning engineer at ETMS, Ario Cecchettini. And since 3 years, I've been essentially working on the field of AI for MBSE. So essentially using AI in systems engineering projects where we're dealing with a lot of Yeah. Yes, is it okay now? Okay, perfect. Yeah, we're essentially dealing with a lot of systems engineering documents. And yeah, we've been investigating some different ways and methods and tools where artificial intelligence, specifically generative AI, can help systems engineering with streamlining their tasks, their workflows, and optimize their outcomes, essentially. So with the advance of technology, of course, even systems engineering projects become more and more complex. Users have more and more expectations, and that leads to more complexity that we have to manage down the line during those projects, right? So at some point, systems engineers won't be able to keep up anymore with the level of complexity that is expected by the users. And the more technology advances, that increases as a problem. And so we've essentially been looking into AI and how we can alleviate these issues to some extent, essentially. So I hope this works. Yeah. Any systems engineers here or requirements engineers or anyone who has been ever working in requirements engineering? Hands up. Yeah, one person. Okay, that's comforting. Who else? Systems engineers, anyone? Automotive business? Okay. Well, so essentially, systems engineering is about the design, the management, and the integration of complex systems, to put it short. And as I said, complexity is increasingly becoming a problem in those projects. And we want to somehow streamline that using artificial intelligence, specifically Gen AI in some use cases. So this presentation is mostly about Gen AI, but there are also some examples where we realize that Gen AI may not probably be the optimal solution, and you may want to opt for another solution like discriminative AI that you can use for specific tasks, essentially. So here you can see, so we 3 steps called Sys1, Sys2, Sys3. Within a systems engineering lifecycle, this is what we call some of the processes there. It starts with requirements elicitation, then you continue down to requirements analysis, and then you actually start doing the system architecture design. And across all these steps, there are some major hurdles and some major issues that the engineers need to overcome. In very large projects where you have hundreds or hundreds of thousands of artifacts even, it's very hard to manage all these assets and documents and requirements, right? And at each step, there are some specific hurdles natural to these steps that may carry over to the other engineering steps like development and testing and so on. And we may actually end up delivering a system that the customers actually didn't want. And in order to prevent that, so one thing that we know by now is very important is to start working on the issues where they occur. So if we have an issue occurring in requirements elicitation, which is one of the major blocks of problems to arise, instead of allowing it to carry over, we can actually use artificial intelligence to alleviate these issues from the get-go before they even carry over to the other engineering phases. So, and then there's a 4th step here, assisted search in PDF documents or informal models. As with many other jobs, systems engineers need to deal with a lot of documents, essentially. So this is not a systems engineering step per se, but something systems engineers need to essentially deal with all the time. And there are some Gen AI solutions here as well that can help you get the necessary insights from the documents at the moment that you need them, instead of having to scour through all the documentation and the assets that you need to work with in a project. And so with that being said, the first use case, requirements elicitation. So just to give you a bit of background on this, requirements elicitation is where you essentially take the requirements from the stakeholders or from the customers. They are being written down in this case, and then you consolidate them to understand what the client wants, right? And these requirements are then stored in a database like IABM Rational Doors, one of the major go-to solutions. And we have other tools now like Doors Next that is being used to store all of these requirements. And within this step, more than 56 percent of systems engineering issues actually arise during the very first step, and they carry over to development. And the reason is that all of these requirements we are eliciting, they are written by human hands. They are natural language sentences, essentially. And we have no way to test it because we didn't start development yet. But there may be a lot of issues ingrained within these sentences that may carry over. So, and with very large projects where you have thousands and thousands of requirements engineering sentences, this may become a huge problem, and there may be a lot of issues that carry over. So one way we realized people can do this and systems engineers can alleviate these issues is to having a few issues with, is to use some classical natural language processing tools in combination with Gen AI to actually generate what we call a unit test case. Any developers here who heard about unit testing? Okay, good. So just same way you would be writing your test cases for your code, we can use Gen AI in this case to actually generate test cases for our natural language sentences. And the way this works is, you basically build what we call a natural language processing pipeline that takes the data, feeds it through an AI model. In this case, this is actually a small language model that you can actually use for this case. And so you don't even need to work with large language models all the time for all use cases. In many cases, it's actually enough to use a small language model. The benefit of that is that you can run it on your CPU. It's computationally speaking a lot cheaper, and you still get the results generated that you need. And the nice thing about some of these small language models that we can already use for this task are so accurate in the way they generate the necessary information that they barely make mistakes anymore. In this case, one thing we do is to generate so-called grammatical parse trees, because with these grammatical parse trees, we can see how a sentence is formed and then make decisions on how well-formed this requirement sentence actually is. Who heard of INCOSE? One person, okay, International Council on Systems Engineering. They have written essentially a guide that helps systems engineers, requirements engineers with writing really good systems or software requirements. And what the additional step that you can take here essentially is to incorporate this additional information into this model and then generate even more fine-grained test cases for your sentences. And then you can basically batch feed all of your requirements batch by batch to the system in order to get all the necessary parse trees and information to decide whether or not that specific requirement is well written or not. And then your engineers can either review them themselves and rewrite these requirements themselves, or if you want to, a bit against my philosophy, you can also take this down further and that Gen AI form the sentences for you. But ideally, you want to use Gen AI as a checking method for these requirements. So to give you an understanding of this, okay. Few issues today. Yeah, so as you can see here, I have a couple of requirements. Here's some very basic ones for demonstration purposes. A picture shall be recorded, for example. In this case, of course, we can say that this is a very well-written requirement. And let me go back a bit. Yeah, so you see a picture shall be recorded. Of course, this is a very poorly written requirement right now. And we need to find out, first of all, why is this requirement badly written? And down below, you see the test suite that was generated. So first of all, it is written in passive language. And it's missing a subject, essentially. So these are actually, for requirements engineering, we always want to write in active form, and we should use a subject and an object, basically, in order to form our requirements. If you don't do that, any good requirements engineer would tell you that this requirement isn't really well written because we don't write requirements in passive form at all. And these are some of the checks that we can do. But let me continue this. Then we have another example the car shall drive fast doesn't tell me anything as a requirements for systems engineering, what I'm supposed to do with this requirement right now. It should at least tell me the car shall drive at 50 kilometers per hour, for example, in a given scenario. Then I could consider this requirement to be a good requirement, for example. And in this case, it doesn't do that. And the test case that is generated here tells me the things that are wrong with this requirement. I'm using a weak verb fast in this case. Instead of using a weak verb like fast, I should actually specify the speed with which the car shall drive in a given scenario. So those are really simple examples, of course, not actual requirements. But this is essentially how you can generate test cases around your requirements in systems and software engineering. Now, if I go a bit further, yeah, in this case, it's actually mentioned that it's driving with 5 kilometers per hour. However, and so it only gives me a warning in the end. So I actually specified the fact that it's supposed to drive at that speed. And in this case, the weak verb is only given as a warning because I already specified what's important for this requirement, essentially. Yeah, so this is one way of doing requirements elicitation. After you gather your requirements from your stakeholders, you feed them to a database, and then you apply the model to that database on each entry in order to generate the test cases. And then developers can essentially be notified on how they need to rewrite their requirements without having to spend too much time on actually identifying the issues themselves. So that really cuts costs, and it also cuts on time, and you make sure that the requirements engineering phase of your project is actually going to be done much faster than before. So much for requirements elicitation. I hope I can somehow. Yeah, and the next phase of requirements engineering would be requirements analysis. Here we have now basically analyzed our stakeholder requirements, take them to the next phase. And what we have to do now is to write a bunch of new requirements called systems requirements. Now, the difference is that stakeholder requirements are basically conveying what the user is expecting from the delivered system in the end. System requirements tell us engineers how exactly the system is supposed to be written to satisfy the expectations of these users. So they are a lot more technical in nature. If you would read them, a stakeholder requirement would sound like more of a business style written sentence, a business requirement. And if you read the system requirements, they are very much more technical in nature, essentially. Yeah, so for requirements analysis, there are a couple of things we're doing. We also try Gen AI. Actually, in this case, Gen AI is not one of the best solutions that you could use for a systems engineering project. There are some other things you can do depending on the needs and requirements of your company and what you need to deliver. So there's one very important core aspect to modern AI and deep learning. It's called similarity. So every time we want our AI to understand textual data, of course, the AI doesn't understand this textual data directly, right? We have to somehow convert it into a format that AI understands, and this is what we refer to as a vector space model. So essentially, all sentences get encoded by a encoder model, as we call it. It is mapped into vector space. So for each sentence, you have a vector of some specific length, and that is a representation of the sentence. And if you have a really good pre-trained model, it can make really good predictions for the values within this vector. So this is how we generate other vectors. And if we stack them together, we have something called an embedding matrix. And this is what the AI actually understands when it's processing natural language data, right? And then there's the concept of similarity. So once we have our embedding matrix, we can actually make comparisons within this space between each pair of vectors or a group of vectors in order to see how similar they are. So if I have 5 requirements somewhere in my database, and if I have vectorized them, I can now see how similar these requirements actually are to one another. So I may be able to find duplicates with this in this case. So if I have 10,000 requirements, there's a high chance that I'm going to end up with so-called zombie requirements or duplicates that are not supposed to exist. So for a system requirement, I should only have one instance of the system requirement and not more than them. And that way I can easily remove all of the duplicates. I can also measure similar. I can also measure how similar two requirements are if they're not duplicates. So even if they have no lexical overlap, and the wordings within sentence A and B are very synonymous to one another, but not exactly the same words, I can still have a really accurate measure of similarity between my sentences nowadays with the current models that we can use, essentially. And the other thing is classification and categorization. So this is not Gen AI. This is actually discriminative AI. And so the reason why I want to show this is because in some cases, I mean, as great as Gen AI is, for some use cases, it's great. For some other use cases, it's not so great. So maybe in some use cases, you actually want to backtrack to use more classical methods to artificial intelligence, like supervised learning, where you are actually building a model to classify, to work on a very specific task, that classification, essentially. And in this case, but you see, and one note about the UIs, these UIs are basically just made for demonstrations like this. It's not a product in any way. So we designed these UIs to make it more easy to grasp what we're talking about here and what you can do essentially in your organization to streamline your work. Let me see if I can manage to click on this again. So what you see here is an example of supervised learning, essentially. So we had this use case with one of our clients that they wanted to classify a lot of requirements into different security relevant, cybersecurity relevant categories. And essentially, this is one of the ways that you can do that, right? So you can even do it with Gen AI, but it might be more accurate in this case even to do it with a supervised model, because that increases the risk of hallucination when you're actually doing the classification into different categories. And we need that structure later, actually. So yeah, as you see here, so there's one example, the right for each user to operate functions and to see data on different, yeah, it's gone. The system must allow the user to limit access to cases specified and so on. And then the predicted class is access control, for example. So this is one other way of building an AI model from scratch to actually make classifications like this. It's not a use case that occurs in many organizations, but it does occur in some very large organizations where they have to do such classifications. You could use LLMs for that. You could use generative AI for that, but at some point, you want to sit back and think to yourself, am I hyping this right now? Or is there a more accurate and precise solution to the specific problem that I'm having? And in this case, actually supervised learning might be better. Yes, so this is how we do supervised learning. And in the next example, give me one moment. Okay. Right, this is supervised learning. And then in the next step, what we call system architectural design, this is where actually generative AI, we realize this is where it actually starts to really shine. Because what we do here is a bit of more creative work. We want to create architectural diagrams from scratch. And this is where Gen AI really proved in many use cases that it is able to generate pretty accurate architectural diagrams that we need in software and systems engineering. And so in this case, I would say, okay, definitely go for Gen AI and don't go for any other types of models, because Gen AI just works out of the box. You can connect it to your systems. You can more easily nowadays build integrations into the tools that you're using. And that in turn is going to allow you to build these architectural diagrams. So in SysOne and SysOne, we essentially elicited our requirements. We have analyzed them. We have categorized and structured them. And now is the time to move things forward to actually create an architectural diagram out of our requirements, right? So here, what you can do is to have a chatbot-like feature again, like so similar to ChatGPT, but only on-prem on your enterprise setting, essentially, where you give the AI a prompt and it generates a basic architectural diagram for you that you can then even update. That's the cool part about this. You can actually say you want to add a brightness variable and a way to increase and decrease the value. And then it just updates the diagram with the additional logic and stores it. So then as an system architect, what you have to do in this point, instead of designing everything from scratch, is that you just generate this template, this boilerplate architecture for you, and then you essentially make modifications down the line. And you can imagine that this is a much faster process to architecture building than compared to building things from scratch, right? So even if there are small mistakes in this case, I mean, you would have to review it anyways. You can make edits down the line. So this really streamlines your work. And this is essentially one more way with which you can actually save a lot of time. And I mean, in large projects, these 3 steps can take a lot of time. And even if you are able to use these methods to reduce the time your engineers need for that stuff by 50, 60%, that's already a lot. Yeah, so this is one way of generating a formal model. And then there's another way of doing that. I'm not going to play the video now, but you can already see it. So it's a bit small, but essentially what you see here are a bunch of system requirements. And you can use, again, AI, generative AI in this case, to generate an activity diagram out of it. So the model doesn't have any understanding of any structure. It only takes the requirements as they are and latently understands the structure and how these requirements are related to one another from the sentences directly. So this makes your work even easier because you only have to feed a batch of sentences to your AI model and it will automatically generate the right diagram. By the way, we checked those diagrams, they're actually correct. So for tasks where you have to be somewhat creative, generative AI pays off a lot. If you have to be really, really precise, like categorizing requirements into different buckets of categories, for example, you may want to opt for supervised learning because it's just more accurate and you have built a model that really is specialized on doing only this task, right? And yeah, so much for the architectural diagrams. And then, as I said, there was a additional step. One moment. And that's assisted search in PDF documents and formal models. So as in many other jobs, you constantly have to deal with a lot of documentation. We have a lot of requirements we have to deal with. We deal with something called specification documents. A lot of the requirements we're allo setting are actually written down within these specification documents. But the problem is that it's never the case that all of our requirements are written in a specific designated section of these specification documents. They're usually, like in most cases, even at the big enterprises, scattered all over the specification documents. So it's very difficult to extract the insights that we need when we need them. And one way you can do that, I mean, of course, in this case, you wouldn't want to feed all your data to ChatGPT because you need to think this is your private IP protected enterprise data, and you don't want to feed everything to ChatGPT to give you the necessary insights. Plus, the ChatGPT model doesn't have any understanding of your company data. If you have kept it private, well enough that is, it's not going to have an understanding, and it shouldn't, right? So what do you do in this case? So there's a solution called RAG, Retrieval Augmented Generation. Who has heard of this? Okay, a lot of people, great. So in this case, well, I don't have to do much explaining then, but for those who don't know, essentially you can deploy your own large language model on premises and stack your external data to this model in order to generate a more precise and well-written and accurate answer for the specific question you are asking about your own enterprise data. The good thing is that your data is kept private, your LLM is on-prem, so there's no data flowing outwards outside of your company. It's all inside the company. And you still have a really good quality chatbot in the end that you can use for getting the necessary insights. You can combine this with classical semantic search even, where you're not receiving a generated answer for the model, but are actually getting the source documents returned based on the query you're inputting. So if you work with Microsoft Bing and so on, right, there's this nice Copilot feature now. This is how you can think of RAG a bit, but in a private enterprise setting and not on the internet, essentially. So the way this works is you feed all of your data into an encoder model. As I described, it gets encoded into vector space, and then you persistently store all of these vectors within a so-called vector database, right? And to give you an architecture, this is how it looks like. So this is your normal chat prompt workflow, right? You have your user prompt, and then you receive a answer from the LLM. Like this is your usual chat GPT stuff. And on the right side, you're actually slotting your enterprise data to the LLM. That does not mean that we are training or fine-tuning the LLM or an external data, or that the LLM even actually incorporates that information directly into its understanding of the language. It merely stacks together its own knowledge from the language and from all the data it has seen with the company information that you have in a separate step there, which is prompt plus relevant data, and then generates an answer for you, essentially. So this way, this really decreases the likelihood of the model to hallucinate and gives much more better domain-specific answers down the line if you work with that. So even this RAG architecture, this is actually a very, very simple architecture. I mean, in an industry setting, we would go much further and have a more complex architecture to design this RAG feature. There are different ways to do that, and there are many different tools that you can use. There are many different solutions to vector databases that you can use. There are many different LLM models that you can use. So you can mix and match things kind of together and see what works best for your specific enterprise data. So of course, there's a lot of trial and error involved because every data is different. You need to, the key point here is your organization's data, and that you need to understand what works best for your organization's data in terms of large language models, in terms of which how you store the vectors, how you cluster the information together, and so on. So, and the good thing is it's computationally really cheap because you don't have to actually fine-tune a model. You don't have to train a model. You merely put your data into vector space and then stack things together. So you could run this on your CPU, actually. So you could even use a small language model even to do the encoding for you, for example. And so that makes it really valuable for a lot of companies in this case, because they don't even have to fine-tune or train a model from scratch. You just literally just have to build a software chain that stacks the necessary components together. And then you can have your private enterprise-ready chatbot that gives you the insights that you need at the right time, essentially. And here, yeah, so there are some drawbacks, of course, with using large language models. And as I said, so the title of this presentation is Gen AI for Systems Engineering, but I also talked about a few ways where Gen AI is applicable, but you may want to consider to also try out other solutions that are not Gen AI, that might be what we call discriminative AI, supervised learning, essentially, in order to solve your problems in a more specialized manner. Because some drawbacks with these large language models is carbon emissions, greenhouse gas emissions. That's one of the big topics right now. And as you can see, there are 552 tons of CO2 equivalent emitted for training GPT-3 model, and that's like 700,000 liters of water. So it's a lot of energy that we're using there. It's a lot of energy we're consuming to train these models. And in many cases where you can indeed use an LLM to get the job done, if you would play around it, you would realize you could actually go for a much, much smaller model to get the task done for you with exactly the same quality. Like, for example, semantic search, there are models that are much smaller and much more compressed for the task, and that by far don't need much compute power or energy. And classifiers, I mean, we had cases where classifiers in the end were only 2 megabytes big, so that's nothing. So as you can see, this really puts much less of a strain on your compute capacities. and you can work much more efficiently and even install things on the local devices um, of your employees or your business people and so on to work with. Um, yeah, so here I mean, if you compare this to a human, it's like 7.2 only compared to a round trip Berlin to New York, that's 2.3. And an average lifetime for greenhouse gas emissions from Mercedes-Benz is 47.9. So you can see how much training these large language models are actually consuming in energy terms. And I mean, finding the right solution is not just something you want to do for your company for the sake of better results and better output, but also for the environment. Yeah, some additional aspects here. So legal and compliance issues, again, like RAG is one of those beautiful examples that could potentially solve a lot of your legal and compliance issues because you're not feeding any data outside of your company. It's all in there. You're building a local RAG system, everything stays there, and you have to deal a lot less with such issues. There are still issues, there are still things need to be green lighted in larger enterprises. You need to gain permissions in larger enterprises to use certain tools. But compared to using ChatGPT or any external API really to using your model, this is a much better solution essentially. And then there are security concerns. This all goes back. Do I want to use on-prem? Do I want to use an on-prem system, or do I want to rather focus on keeping things locally essentially? Yeah, so those are some of the additional aspects. And we're above time right now. Thank you very much. And I would open the round for questions. Any questions? I mean, for small projects, it works very well. For large projects, it comes down to how much compute capacity you have, because the more data you have, of course, the more stuff you have to encode into vector space. And that's going to put a lot more strain on your compute power. Even if you're using a small language model, it's going to take much longer to encode everything, right? So these are some of the factors you want to consider, so that you can at least feed your data batch-wise to the model so that you can get all of your data encoded faster. You need a distributed system for your vector database. So you have different nodes for your vector databases, in this case, where you store all the data. So you need a lot of storage capacity, of course, so that all scales. And you need to look out for those things. But otherwise, it works. Yeah, yeah, comparatively speaking to what we call now a large language model, they are much smaller. Yeah. So for example, there's one model called Roberta, which is a model that was specifically trained and fine-tuned for generating these parse trees in one instance. There's a version of this model that does that really well. There's an open source library called Spacey for natural language processing, where you can even use it out of the box. And it generates the parse trees for you in Python code, and then you can essentially build the decision-making around the parse tree. That's something else. For that, you want to have a different type of model, actually, that is really good at encoding all of your data for the purpose of semantic search. Because Roberta, for example, is not so good for semantic search. There are other models that are trained from the ground up for doing semantic search, like SentenceBird, for example. That's one of the go-to models in the industry right now. And if you want to do that, if you want to do semantic analysis on how similar two sentences are, for example, two requirements are, you may want to opt for SentenceBird. Yeah. Any other questions? That are not what? I'm sorry. I didn't get that, to be honest. No. Oh, contradictions. That's a bit harder because That's a bit harder, actually. This is something we're actually going to work on. So I can't give you a straight answer right now because it's much harder. Because on a scale, you have something called semantic similarity, which is a metric. And the minimum of that is -1, and the most of it is 1. If you have 1, you have a duplicate, right? But if it's below 0, if it's closer to -1, that doesn't necessarily mean that those two requirements are contradictory to one another. So it's a bit more complicated to do that. And this is actually one of the things that we're currently researching.